Okay, so it's a great pleasure to introduce Professor Patrick Massot um, from Université Paris-Saclay, and he'll
Mhm.
be speaking on formalizing differential topology and geometry. Welcome.
Yes, thank you very much for the invitation. It's nice to get an opportunity of talking about all this to people who specifically care about differential geometry and differential topology, as I've been told, because usually I cannot assume any knowledge of those mathematical areas when I give formalization talk. And so today I will assume that you know at least a bit of differential geometry. So you should not be frightened of hearing something like vector bundle over a manifold and something like this. So, and don't hesitate to interrupt me because I cannot see you while I talk, and I've got many little stories to say. But there is no big surprise at the end, so it's not a problem if I don't have time to discuss everything I prepared. We can just talk. So the starting point for me of the formalization of differential topology in Lean was the sphere reversion project. And so the context of this project was we know we've known for a long time since 2012 that you can do non-trivial algebra in a proof assistant, so namely in ROC, formerly known as COC. So they did the odd order theorem, was very impressive, and many mathematicians got the idea that those proof assistants they were good enough for logic and algebra and combinatorics, but what about real mathematics? What about differential topology, for instance? And that was really the question that we wanted to answer in this sphere reversion project that ran between I think 2022 and 23, I think. Um, so there are obstacles if we want to do differential topology. I was pretty sure we could do differential topology, but maybe it would be indeed a bit less easy. So the first kind of obstacle that you think about is maybe they are proved by geometric intuition. Maybe people don't really prove this existence of turning a sphere inside out because we just draw pictures. And indeed, there are a couple of proofs like this where we had to just give arguments for things that are geometrically obvious. But honestly, this is not at all the main problem. The main problem is constructions with vague input and output. So when we have some geometric construction theorem like the existence of the sphere reversion, so turning the sphere inside out, the issue is you don't want to do the construction in one go. And the output of the full construction is clear, but there are many intermediate steps. And if you read traditional text about this, the input and output of those intermediate steps are not completely clear, or maybe the proof is not completely correct. And the tricky part is to get statements that are 100% correct and useful. It's kind of easy to get one of them, either really correct statements that are not quite what you need for the remainder of the proof, or something that is clearly sufficient for the remainder of the proof, but not quite correct, meaning maybe there are missing assumptions. Or also missing conclusions. You do not record enough in the conclusion, and something is a detail of the proof that will be useful later and not stated in the statement. So those are obstacles, and also general obstacle for any formalized mathematics is proof mixing up bureaucracy and actual content. So I will give examples of this, so hopefully this will become very clear during the talk. So that was the challenge. Do something non-trivial in differential topology, and of course, there was also a public relation aspect. So many people know about sphere reversion because YouTube is full of videos of concrete sphere reversions, and they look paradoxical. So that was kind of the reason to choose that. So I will describe lots of things around those questions, but I already note it's very hard to compete against non-proofs. And there is nothing more efficient in mathematics than not proving something. And I will explain some stuff, and maybe you will think, I don't need this. And why don't you need this? You don't need this because on paper or during a talk, you would normally never explain anything about what the proof is about. So of course, I cannot convince you that writing a formal proof is more efficient than completely skipping the proof. So keep that in mind for the talk. I want to say also, before we zoom on details, zoom out a bit and remember we have many reasons to formalize mathematics. I think you had talks about that earlier in the season, so I won't re-explain every reason, but I want to single out two reasons. There is the obvious reason of checking proof correctness, and this is completely useless for the sphere reversion project. There was no doubt at all that you can turn a sphere inside out, and the project was not at all about checking whether smell indeed had a proof of this theorem or nothing like this. Something that is always useful, on the other hand, is clarify understanding and, more importantly, communicate this understanding to colleagues, especially beginners. And by beginners, I mean beginners in differential geometry, for instance, so not necessarily first-year undergrads. I mean, maybe early graduate students or people like this. And there are other reasons, but today's talk will be really focused on clarifying understanding and explaining what we are doing. So just recall, I've been saying sphere reversion for a while, but just to make sure everybody is on the same page, what I mean is Smell sphere reversion theorem. So there is a one parameter family of immersions of S2 into R3, which starts at the inclusion map and ends at the antipodal map. So this is what I call the sphere reversion theorem. And just assume you understand the statement, but those maps J sub T, they are locally just embeddings of a smooth surface, but self-intersections are allowed.
Right.
Yeah. Is there a question? I heard something. No? Okay, continue. So I will quickly review the proof that we formalized. So how do you turn any map into an immersion in two easy steps? So we start with a map from any map F0 from S2 to R3, and we have some compact set in the sphere in an open set where there is a local trivialization of the tangent bundle of S2. So I've got my local frame E1, E2 of the tangent bundle of S2. So of course there is no such global frame, but locally I can find this. So first step, from my map F0, I build a map F1 such that for every point near this compact K, the first tangent, the first vector in my basis is sent to a non-zero vector in R3. So certainly this is being one step closer to being an immersion, since I want the tangent map to be injective. So I first impose this, and then the second step is I will build a map F2 starting from F1 so that near this compact set, the derivative of F2 in the E1 direction is very close to the derivative of F1 in the E1 direction, so it's also non-zero. And the derivative in the second direction, in the direction of E2, is not in the line spanned by the derivative of F1 in the first direction. And I claim that if I achieve this, F2 is an immersion near my compact set K. And I did it in two steps. First, get one non-zero derivative, and then the second partial derivative is linearly independent from the first one. And make sure that those modifications have support in U, so this open set containing K, and just cover S2 by such a compact set, so you could do with two of them, and that would be fine. So that is the step-by-step construction to build, turn any map into an immersion. So what just happened? So we improved the derivative of f one direction at a time, and the improvement always has this shape. So the derivative of f acting on the EI vector belongs to some open set that depends on x and I. some omega I of x. So, and at every step, I need to almost preserve the derivative of the map in direction that were already improved. And if I want to do that on a manifold, like on S2, I need to do that. I need to build C0 small and relative modification. Relative, I mean, if I already improved my map F on some set, and then I move to another set, I don't want to destroy the improvement that I just achieved. So quickly, the proof, so this sphere inversion statement, I should say, it's kind of a benchmark in differential topology. Anytime you have a geometric construction method in the H principle spirit, you should test it on the sphere inversion problem. So there are many proofs of this theorem, and the proof we formalized uses convex integration. And convex integration, of course, is due to Gromov, but there are many different concrete implementation, and the one we used is by Mélanie Teyer. It's a very recent implementation from 2018. So what is the setup? So it's a completely local process. So no, forget about manifolds for a while. We have a compact set inside an open set inside a Euclidean space, and a map from the open set to R to the D, another Euclidean space. And I want to improve the ith derivative of F0. The ingredients are a family of loops in the target space indexed by the source open set. And each of those loops, they take value, so individually, so when I say family of loop, it's really a map from U times S1, but I see it as a family of loops gamma sub x, where x is in U and the S1 variable varies. So it takes value in this open set omega I of x, that is my constraint for the ith derivative of the map. And the average value of this loop must be the original partial derivative in the ith direction. And from those ingredients, if I can somehow build such a family of loops, then I can perform convex integration. And the convex integration scheme by Mélanie Teyer is this formula. So I've got the original map F0, and I add to F0 1 over n, where n is a very big number, times this integral from 0 to n xi of gamma x of s minus its average value. And I claim that this formula, now you have a very, very nice calculus exercise to do. First, the obvious one, so the map that I'm integrating, this gamma x minus its average value, it has a vanishing average value by construction. So it's when I integrate like this, it's bounded. So when or maybe I should say, when I put s in gamma x, so s is a real number, but I project it down to s1 before filling it to gamma x. And so the integral is bounded. So in C0 topology, the modification is in a big O of 1 over n. And then you do the little calculus exercise. If you differentiate f1 in the j's direction where j is not I, then not much happens. You differentiate under the integral sign, and what you get is still bounded in C infinity topology. So you still get a big O of 1 over n. But if you differentiate in the ith direction, then something interesting happens, because there is also xi in the bound of the integral in the nxi. I'm integrating up to nxi, and so you get a gamma x of nxi that is times n, that is an extra term in the derivative, and because the average value of gamma x is di f0, the di f0 disappears, and what you get is gamma of nxi plus big O 1 over n. Okay, so it won't be super important for the remainder of the talk to really understand this, but you can just note this formula, or I will share the slide later if you want, and do the exercise if you didn't get it. But the important thing is the new map F1 is C0 close to the old one, and so the values almost didn't move. The derivatives I was not interested in almost didn't move. And the derivative I was interested in, the ith partial derivative, is now in omega I x at every point x, because it's almost a gamma of nxi, and omega x is open. Okay, so we formalized this process in Lean. And first, maybe a bit of comment. So, is there hope to find such a gamma? So the thing is, the constraints are we want gamma x to take value in omega I of x, and because the circle is connected, actually it needs to take value in a connected component of omega I of x, and the average value is prescribed. So this open set omega I of x is dictated by the problem, and the target average value is out of control. So that seems a bit difficult unless the target average value is in the convex hull of omega I of x, and that's why it's called convex integration. So in the sphere immersion case, the first omega set is omega 1 of x is just every non-zero value in R3. That's the constraint we put on our first partial derivative. And then the second constraint on the second partial derivative is the complement of a line, the line spanned by the first partial derivative in R3. So both those sets are connected open sets whose convex hull is everything. So this convex hull of every connected component is everything. And so there is hope to find families of loops in this case. So at least for a fixed x, it's pretty clear we can find a loop, and then we need to do it carefully because x varies, and so we need to find a loop with parameters in a parametric way, but this can be done. And, so this is all doable. So quickly, what we actually proved is the Gromov's H principle for ample relations. So when I say we, it's with Oliver Nash from Dublin and Floris van Dorn, who was at that time a postdoc in Orsay, but is now in Bonn, in Germany. So what we formalized is the full H principle for open and ample first order relations for maps between manifold. So quickly, if you're interested, it means instead of just looking at immersions of spheres into R3, what we consider, we take any open set in a jet, in one jet of maps from M to N. So those one jets of maps from M to N, there are a point in M, a point in N, and a linear map between the corresponding tangent spaces. And the goal is to build sections of R that has this special shape M goes to M, f of M, and derivative of f at M. And so we want to build a map such that this section lands in R. So for instance, in the immersion case, R is the set of triple where the linear map is injective. And the ampleness condition is this: every time we fix a hyperplane in any tangent space to M, we look at the space of linear maps coinciding with a fixed one on this hyperplane and belonging to the constraint to the relation R, and we ask that this constraint is ample. So this set of linear map is ample, and it means every connected component has full convex hull. And hopefully, with the previous explanation, you can kind of see why this tells you that the convex integration technique will work on those problems. And when I say we do the full H principle, it means not only every section of the relation is homotopic to a section coming from a map F, but also we do it with parameters, so which is of course crucial for the sphere inversion case, which is a one parameter construction of immersions, and also relative to subset and C0 dense, I mean the full package, full flexibility of this problem. Okay, so that was the sphere inversion project. So that just the goal here was to give you an idea of what is already possible to do in differential topology in Lean and was already possible 2 years ago. And now what I want to describe is what kind of changes it makes compared to paper proof. I mean, this explanation I just did, I could have done without any reference to Lean. So what is slightly different when you do it in a proof assistant and when you do it in a formal way? So there are many more lemmas that you need to state to keep the complexity under control. And so let's take a first example about inductive construction. So let's say I've got a vector bundle over a manifold, and P is a predicate on E, so I'm sorry about the logic terminology. So predicate on E means for every element of the total space E, P says yes or no. So it's and I want to build a section of my vector bundle. So I'm leaving out the assumption for now. I want to build a section of this vector bundle so that for every x in M, P of sigma of x. Okay? So this is just a very, very general way of saying I want to build a section of a vector bundle with a pointwise constraint. I have a constraint on the value at every point of my section. So now there could be many assumptions, many kinds of assumptions to put here, but I will put this one. So I assume local existence. For every x in the base manifold, there is a neighborhood of x and a solution on this neighborhood. So a section of E restricted to U, such that for this section is a solution that, for points in U. And so this is a kind of an initialization of the induction, and then the propagation step is fiber-wise convexity. So for every point in the base manifold, the set of vectors in the fiber over this point that satisfies the predicate is convex. And I claim that under those two assumptions, you can find a global solution. So let's do two examples of this. So first, a very elementary example. Let's say I want to approximate continuous positive functions by smooth one from below. So I give me a positive continuous function from M to real number, and I want a smooth one, delta, that is at most epsilon. So of course, this is not a hard result, but let's say I want to prove that using the lemma that was on the previous slide. So I say here the vector bundle is just M times R, the trivial R bundle over M, and the predicate attached to xt is the value t, so seen as a living in the fiber of x, must satisfy t is positive and at most epsilon of x. So this problem has the shape I wanted, so I need to check the assumptions. And the local existence is given by the extreme value theorem. So just pick any compact neighborhood of x, and the extreme value theorem gives you that epsilon has a positive lower bound on k. And so on any open set contained in k, I've got a constant solution, which is very smooth, positive function. And fiber-wise convexity is even easier for a fixed x. The set of t that I'm looking at is an interval, between 0 and epsilon of x. So this is a convex set. And so the lemma from the previous slide applies and gives me my positive function delta. Now, less elementary, but even better known example is just proving existence of Riemannian metrics on any vector bundle. So I start with vector bundle V, so it could be the tangent bundle of M, could be something else, and I want a positive definite field of bilinear maps from V times V to R, and so the bundle E is a bundle of bilinear forms on V, and the predicate is just G is symmetric definite, positive definite, and the proof is again applying the lemma that I had on the two slides ago, and the convexity is the convexity of inner products, and local solutions are given by charts. And of course, this is the way you prove existence of Riemannian metrics in every differential geometry class, except that you don't state the lemma. You don't state the lemma, so let me go back to the lemma. I mean, this statement, I've never seen it written on a blackboard except when I write it or in a textbook, because what people say is that they just repeat the proof forever. So they say we have local solution, we take a partition of unity subordinate to a cover by open sets where I have local solution, and then I glue my local solutions by partitions of unity, And the convexity assumption tells me my partition of unity my glued my section will still be a solution. Okay? But what happens is in the Riemannian metric case, E and P are already getting a bit distractingly complicated. Like this bundle of bilinear forms is already lying around here, and the condition that G is a positive definite symmetric bilinear form is already more complicated than just denoted it by P. And also, if you use the lemma, you really emphasize the key features of the problem. So this kind of local existence and convexity is really emphasized. And for instance, if you want to explain to students that that proof would not work for Lorentzian metric, so in different signatures, well, it's because the space on a vector space, a Lorentzian inner product, do not form a convex set, and so convexity fails. And, uh, and obviously, I'm not saying this will deeply change your understanding of why positive smooth function exist or Riemannian metrics exist, but it cleans up things. And it cleans up things already on paper and much more in a proof assistant. Because in a proof assistant, every complexity that you carry around it has to be paid for. And so if you're combining your local solution using a partition of unity and the bundle is complicated and the predicate is complicated, everything will be much more painful in Lean or in any other proof assistant. And also, you have to repeat it over and over again. If you're doing differential topology or differential geometry, there are many arguments with partitions of unity, and if you don't prove a lemma once, but just keep repeating the proof, it gets very painful in the proof assistant. The reason why it's not getting painful on paper, on the blackboard, is because you don't repeat the proof. You say this is the usual partition of unity argument. And people understand what it means, at least if they know the field. But so first it's painful for beginners, even when you do it on the blackboard, because they don't know what is the usual partition of unity argument. And if you do it in a proof assistant, it's just costs a lot more. So there are more general versions of this story. You can use local predicates rather than pointwise predicates. So it means that P, instead of being defined on the total space of the vector bundles, it will be defined on jumps of sections of the vector bundle. And of course, in the Sphere version project, we needed both versions of this principle. And you need to be a bit careful when stating the more general version, because the convexity condition now involves the ring of germs of functions instead of the field R. And of course, the germs of function is not an integral ring. I mean, you can have zero divisors. So when you say a set is convex, it's not enough to ask that if you've got 2 points in the set, the segment between those points is in the set. You really need to ask that convex combinations, finite convex combinations are the set is stable under convex combinations of any number of points. And of course, when I say it's nice that the partition of unity argument has been encapsulated in an abstract statement like this, I do not say you should forget the proof, because there will always be cases where your abstract version will not be enough, and you need to remember that this abstract version comes from partitions of unity, and maybe you should go back to partitions of unity and do something more specific or more clever. There is always this risk when you abstract stuff away of actually ending up with something less powerful because it would be less flexible. And now the next topic is globalizing charts constructions. I mean, unless there are questions, maybe I should ask for questions from time to time. Do you have questions about this partitions of unity story? I don't even know if there is still someone listening to me.
Yeah, can I
Yeah.
ask a question?
Yeah?
Sure. So you're stating some general statements, and the interested problems follow as corollaries. But where do you stop at the generality? So do you want to go on and on to make it more general? Like, but where do you stop?
That's a very good question. They're of course not specific to formalization, and that's also why I put this warning, this second warning. I mean, sometimes you just, I mean, at some point there is diminishing returns in making more and more abstract and general results, and sometimes you should just do something by hand. But there is no there is no global rule for this. We have fairly abstract results in the sphere eversion project, and some of them are even, I mean, clearly one use abstract result. So it looks kind of silly. I mean, if you look at the blueprint from the sphere eversion project, there is an appendix about globalizing or going from local to global or something like this. And some of the technical statements, abstract technical statements, are really, really frightening. And it's pretty clear we have only one application in mind for some of those lemmas. But even in that case, in the proof assistant, it pays off to do that because again, the abstract version has no complicated notations, maybe also no complicated setup. Like if some part of the argument is actually all about topological spaces and gluing stuff on topological spaces, you don't want to do it on a manifold because just saying in lean let M be a differentiable manifold is really a lot more complicated than saying let X be a topological space. So if some part of the argument does not use the manifold structure at all, but just the topology, or maybe the fact that the topology is metrizable or something, but no calculus, no differential calculus, then you should consider formalizing, even if the abstract lemma looks a bit silly, and just extract the purely topological part of the argument, do it in a simple setup where you won't have the info view. I mean, in the theory version project, the tactic states routinely is more than one screen tall. So it means you can never see, if you display all assumptions, so you can filter out the tactic state in lean, but if you don't do that, you simply do not see the full list of assumptions and objects in your proof. So this is kind of painful. So we do use a somewhat silly abstract statement in some places just to get rid of this complexity.
Okay, okay, thank you.
So something that is systematic in those H-principle proofs, or all those flexibility of geometric construction results, is everything, the heart of the matter is really completely local. So this convex integration techniques, it is fundamentally a completely local technique. So you're trying to build some map satisfying some constraint, or maybe a family of map satisfying some constraint. And the local problem is so well solved that there is no problem globalizing it, because it's solved. You can solve it in a C0 close way. You can solve it relative to a closed set where you've already a solution. And so what people say in differential topology or differential geometry is, you do it chart by chart, and there is no problem gluing things because the construction is so local and relative to closed set where you already have a solution, and so there is no problem. And typically this is one sentence in a book, even in a textbook. If you read Eliashberg and Mishechev H-principle textbook, there is simply no explanation at all about how do you globalize the construction. So we are in this situation. We've got a smooth map between manifolds, and we want to improve F chart by chart. And typically, the pen and paper proof is just to say, yeah, of course, we do it chart by chart. And then if you ask a bit more detail, so here, I'm sorry, I should have a drawing. I mean, on the Blackboard talk, that would be a nice drawing. But here, I've written some annoying to read thing. But So I say you can find an atlas for M and an atlas for N, such that the map F, the original map, sends the charts on the source to charts in the target. So you use, you start with a chart on the target, pull it back by F, which is continuous, and then refine discover by as an atlas, and you get easily such an atlas. So UIs are open sets in M, the VIs are open sets in N, and I should say, sorry, this should be VJ here, and psi j are charts taking value in some norm space F or norm space E. So, and forget about the K for now. Let's say or maybe I say it, inside your source chart, you have a compact subset that still covers. And what do you want to say? You want to say, I start with my map F and just make it a map using the first chart phi1 and make it a map from E to F. So I can assume phi1 is surjective, and so the phi and psi are surjective maps, so that we don't have to care about their images. And now I've got a map between vector spaces, and I do my thing that I know how to do between vector spaces, say convex integration or something else. And I improve it on some compact set on this phi1 of k1, which is a compact set in E. And I do the improvement with compact support. I get a new map, f1 bar, and I replace f by f1, which is just use my charts again to build a new map from M to N. So this is improving F on the first chart, U1. And now I want to move to the next chart, the U2 chart. But the issue is that my F1, my new map, does it still send the open set U2 inside some V of sigma 2, some chart on the target manifold? So of course, if you're careless, there is no reason that F1 still sends charts to chart. And if you, because of course the charts overlap, and you really want to do the modification everywhere, so you cannot avoid the regions where the charts overlap. And if you think about this problem for a minute, you start mumbling things about, yeah, maybe I should take something compactly supported in U, or maybe using this Ki will help, but there is not a clear statement, or at least you do not often see a clear statement of what is the fix. And if you do it in a proof assistant, you need to really fix it. And there is no mumbling with the proof assistant. So there is an easy fix. You can fix a distance function on the target manifold and arrange that the original map, the F map, before any modification, sends every UI to something that is compactly supported to the compactly included in a chart on the target. And then the statement is there is a positive smooth function, so that every function from M to N that is epsilon close to F will continue to send UI inside the V sigma I chart. And of course, there is nothing surprising with this statement. The point is not to surprise you. The point is, if you read a book about the H principle, for instance, you simply do not see this statement anywhere. And of course, I'm not saying that Eliashberg cannot prove this or cannot state this. I'm just saying, on paper, people don't bother stating such things usually. But in the proof assistant, this is the kind of things you need to state and use. And of course, you can you state it and you prove it. And the proof is by what I call induction on epsilon, but this is the induction principle I had before. The constraint is convex, so you can use partitions of unity, but you don't have to say partitions of unity. You say, I use the first lemma I talked about to build such a function epsilon. And once I've got epsilon, then my improved sequence of improvements in different charts will be a sequence of function fi, or I missed fi of x is meant to be fi of x, not fi of x. So when I go from fi to fi plus 1, I do this with a distance 1 over 2 to the I plus 1 or something epsilon, and so that after even infinitely many steps, if my manifold is not compact, I'm still within epsilon of my original function, and I will never get into trouble with charts no longer being sent to charts. So that's a typical example of a statement that you would not write on paper, and you need it if you want to do anything formally. And the last thing of this shape, and this is a little exercise. So what happens when we do this in every chart? We modify the function. And here we need to explain what are the properties of the limit function. If I've got my sequence of function fi, and of course the function improved everywhere on M is the limit of this sequence fi, but it's a kind of a stupid limit because I will do that and near every point the sequence ultimately stabilizes. So it's a boring limit. But I need to say something about how do I deduce properties of the limit function. And what I say is I get rid of manifolds because this has nothing to do with manifolds. So I have a topological space X, a set Y, and a sequence of functions from X to Y. So this is my sequence F, and a sequence of sets V. And I assume that Fn plus 1 coincides with Fn outside the Vn plus 1 set. So those sets, Vn, would be my charts in my manifold. And the claim is simply that if F is locally finite, a locally finite collection of sets, then there exists a limit function which coincides with Fn near every x for n sufficiently large. Again, nothing surprising, but I mean, you can try this little challenge, write a precise proof on first try, I mean, without doing it twice or 3 times. And for extra credit, you can try the challenge of stating and proving a single version where you could replace natural numbers by a finite set. Because when we do this, sometimes there are finitely many charts. For instance, if your manifold is compact, and sometimes there are infinitely many charts. And of course, you could think I could cheat, and then if I have finitely many charts, I take a ultimately constant family of charts. But then if you do that, your family of charts won't be locally finite. So you need to do something. You need to state and prove one version where natural numbers are replaced by either natural number or finite interval, and give one proof that works for everything. Okay, so this is what I wanted to say about those constructions chart by chart. And the comments I have about this is what we gain from going through those trivial lemmas that clearly have no deep content is actually many things. So we can really cleanly separate the routine generic arguments from the actual content. And this is really helps uncluttering the tactic state display in Lean, but also, I mean, remove clutter just in your mind when you think about the arguments. And very often, those lemmas that I stated, they replace non-existent proofs on paper. And they are kind of non-existent for good reasons. I mean, if you're doing non-trivial differential geometry, you don't really want to spend time proving something as stupid as what was on this slide on the limit function stuff. I mean, you don't want to interrupt a differential geometry paper with a proof of this statement. So I'm not saying that the papers are bad, but I'm also saying that if you think I've never had any use for those lemmas, what is he talking about? It's probably because those lemmas replace stuff that you simply do not prove on paper. Not because you're a bad mathematician, but because on paper you would just skip that, and that's there. But in a formal setting, they are crucial. They are crucial because you're not allowed to skip any proof, and and you want to keep complexity under control. And it has some mathematical content, not much, but it has some mathematical content. If you try to find the right statement on first try, or write a precise proof on first try, I mean, unless maybe you have the right mindset and training, I claim this is not completely obvious. And this takes time to get it right. And again, right means 100% correct and 100% sufficient for the remainder of the proof. And last comment is, to me, it seems completely out of reach of auto-formalization. So what I mean by this is, if you take just a traditional paper proof of those results, so say of the H principle for open and ample relation, or the special case of theory version, those lemmas, they are not stated at all. And I don't think, so I don't know, let's say this one, I don't think that auto-formalization model will, I don't know, read a textbook. Even a careful textbook is not about being careless. I mean, even I saw Jack Lee was in the audience, so he'd say you take a textbook by Jack Lee, and those are very careful textbook. I don't think you see any of those statements in those textbooks. So even if you train a model to formalize based on those textbook, I think the model does not give you those lemmas so far. And then you can do science fiction and hope for auto-generation of those statements, but so far this is a completely human part of the process that seems out of reach of current day auto-formalization. Okay, so that was about really specific differential geometry, but then there are also less specific things that I like when formalizing differential topology or differential geometry, which is the need for generalized sets. So when we do mathematics, and especially differential topology or geometry, we need to efficiently say things like for all n large enough, P of n holds, or for all x near a compact set K, say P of x holds for some predicate P on your manifold. And there is no ambiguity about what it means. I mean, the meaning is completely clear when we say that on paper. The first one means there exists a capital N such that for all n bigger than capital N, P of n holds. And saying for all x near K, P of x, it means there exists an open set containing K, such that for every x in this open set, Px. So when people write in differential geometry papers or textbooks, for every x near K, whatever is true, it's not sloppy, it's not imprecise. I mean, it's very clear what it means. The problem is that we need to argue about things like, for instance, if you know for n large enough Pn and for n large enough P prime n, then you get that for n large enough Pn and P prime n, so those are the logic symbol, the AND symbol, logical conjunction. And of course it's true, because if you have the first property P starting from capital N and the second property P prime starting from capital N prime, then starting from the maximum of N and N prime, you get both. No problem proving that. But the problem, if you reprove that over and over again in a formal setting, it's completely unmanageable. Because redoing this proof over and over again, it is pure bureaucracy. And we cannot afford that in a proof assistant. The reason why we can afford it on paper is because on paper, we simply, again, don't write anything. We say we know for n large enough Pn and for n large enough P prime n, and then casually use that for n large enough, both property holds. But we need something in the proof assistant to handle that for us. And the problem is we don't have enough subsets. There are no subsets of all large natural numbers, and we need to fix that. We need more subsets of natural numbers, more subset of our manifolds, and more subset of any set. And the answer is really everywhere in MathLib and in other proof assistant. We know we can enlarge the power set of X for any set. There is an embedding of partially ordered set from the power set P of X into something larger called filters on X. And those filters on X, they are generalized subsets of X. And those generalized subsets, they include the generalized subsets of very large natural number, or the generalized subsets of points that are close to x0. And those things, they do not live in the ordinary power set of X, they live in this larger gadget, f of X, filters on X, and everything extends. So, and what needs to be fixed with the ordinary sets? So the power set of X, so the set of ordinary subset of X, is a complete lattice. So you've got intersections and unions. So every set of subsets has an infimum and a supremum. So the infimum is the intersection and the supremum is the union of those subsets. So that's nice. You've got union and intersections, but the intersections are broken for our purposes. Even the filtered infimums, so you can think decreasing intersections if you want. So for instance, we would like the generalized subsets of very large natural number to be the intersection of all the rays n plus infinity for every natural number n. But of course, if you take this intersection in the power set of natural numbers, you get an empty subset. And if you consider the intersection of every neighborhood of x0 in a reasonable topological space, you get the singleton x0. And those are kind of broken intersections and broken filtered intersections. So filtered means you take the intersection of a non-empty collection of subsets, and whenever you have two subsets in your collection, there is a third one that is smaller than both. This is what filtered. Sometimes people say directed subset means. So left directed or left filtered subset. Okay, so we need to fix that, and this is what the gadget is doing. So the filtered intersections in filters on X are free in the sense of category theory. There is this universal property. Whenever you've got any order-preserving map between the power set of X and any ordered set Z where a filtered infimum exists, say maybe it could be another power set or something like this. Then there exists a unique extension, phi bar, through this inclusion map. So recall the capital P is the inclusion of ordinary subset into generalized subset. And it's an ordered set embedding. And so phi bar really is an extension of phi to generalized subsets. And it's unique if you ask that it commutes with filtered infimums. And so the existence of this extension means that somehow the filtered infimum in the larger gadget are formal, are free. And in addition, this extension procedure is order preserving, and from this you can deduce. So order preserving means if you've got phi on psi and the phi is less than psi, then the extensions are also pointwise. Phi bar is less than psi bar, and it implies adjunctions extend. So what do I mean by adjunctions here? So if you like category theory, I mean I see my order preserving set as functors between the categories associated to those posets, but in this poset setting, it's completely elementary. You've got a function from A to B, L, and a function R from B to A, saying they are adjoint, means that for every AB, L of A less than B, if and only if A less than R of B. So you can move L from the left to the right of the inequality sign, and you go from left to right, you get R, and you can move R to the left and get L. So those are, by the way, this notion of adjunctions for maps between posets is also everywhere in every formalized mathematics library because it's extremely convenient abstraction. What are examples of adjunctions? Well, direct image and inverse image are examples. So if you've got a map between two sets X and Y, you get direct image from the power set of X to power set of Y, inverse image from the power set of y to power set of x, and those maps are adjoint in the sense of the previous slide. And this adjunction, it extends. So you have a notion of direct image of filters and the inverse image of filters, and this diagram commutes. And there is a unique such extension, and they are still functorial the way you think they should be functorial. And this is used everywhere in MATLAB, not only in differential geometry. It's not even only in topology, because I mentioned as generalized subsets, the generalized subset of very large natural number or generalized subsets of points that are close to x0. But if you have a measure space, you also have the generalized subset of almost every point, which is also living in this f of x gadget. And you can use this to discuss convergence in a much more intuitive way. So if you've got a map between topological space, saying direct image of a neighborhood of x is less than neighborhood of f of x, it means really, I look at the direct image under f of a generalized subset of points that are close to x is contained as a generalized subset in points that are close to f of x. So this is really the intuitive way of saying f is continuous at x. It sends points that are close to x inside the points that are close to f of x. And it's both more intuitive and more algebraic. So there is no quantifier at all in this inequality. So, and this is a very general theme in formalization. Just hide as much quantifiers as you can, because just juggling with quantifiers, I mean, you can do it, of course, but it's time consuming, and it's just needless complexity. And all common notions of limits correspond to those generalized subsets. And now I wanted to return to my quantified statement. So now I can define when I have a set and a predicate on this set, so the predicate is Q because P is already taken by the inclusion of ordinary sets into generalized sets. So, and I've got F, which is a generalized subset. I can form the statement for all x in F, Q of x, and the for all is decorated with a superscript F, which means filter, because as an ordinary for all, it does not mean anything, because x and F are not in the correct set for this to be meaningful. But this notation, that should be, again, really read as one block, it means f is less than the set of points satisfying Q seen as a generalized subset. The capital P, remember, is the inclusion of ordinary set into generalized set. So P stands for principal. So principal filter associated to the set of X such that Q of X is greater than F. And you can also do the existential, but I'm not using it today, just mentioning you can also do it. And this notation, if you take a generalized subset that is the image of an ordinary subset by this P map, you get back the usual statement. You get back for every x in A, Q of x. And now that you have this notation of a generalized quantifier, the theory guarantees it will be well behaved, and you have facts like this that you need to prove only once. If you've got two predicates Q and Q prime and a generalized subset F, if you know that for every x in this generalized subset Qx, and you know the same thing for Q prime x, then for every x you get both. And so, for instance, if f is the generalized subset of a very large natural number, you get the statement that I had before. Or the set of points that are close to k, you get the statement that I had before. And same for the implication and the kind of modus ponens. If you know qx and qx imply q prime x for every x in f in this generalized sense, then you get the conclusion for every x in the generalized subset f, q prime of x. And you need to prove those things only once for a completely abstract capital F. And this is really very, very efficient. So, and you get, as an example, if you know that for every x near k, qx, and for every x near k, q of x implies q prime of x, then you get that for every x near k, q prime of x. And if you wanted to prove that by hand, you would say, okay, I get a first open set, open neighborhood of k, such that q, and then I get a second open neighborhood of k, such that q implies q prime, and then on the intersection, I get q prime. And of course, I'm not saying you would not be able to prove that. I'm saying that the formalism of filters and generalized quantifiers give you the abstraction that avoids repeating this proof forever. And this proof that on paper you would not repeat, but you would not repeat it because you would just write this sentence without a proof. And that's totally fine on paper. So if you want to formalize topology or differential geometry in Lean, you need to learn about this technology because it's used everywhere and it's really, really convenient. And I think this is what I wanted to say. Oh, and I've got one last comment about the intuition that you get. So it's not only that you get rid of proofs that you do not want to write, it's also great for intuition. For instance, if you have a topological space and a subset A, saying that A is open means for every x0 in A, the generalized set of points close to x0 is in A itself seen as a generalized set. So this is how you read this. PA is A seen as a generalized set. This inequality is the extension of inclusion to generalized set. And so it really means points close to x0 are in A. And I said the generalized subsets are still a complete lattice, so there is an intersection operation, there is an infimum operation, and you can say, using this operation, that A is closed if whenever the set of points close to x0 intersect A, then x0 is in A. Or X is Hausdorff if whenever two points have intersecting sets of close points, then they are the same, or what I've written is a contrapositive. If X and is not X prime, then those generalized subsets do not intersect. And here I wrote the intersection symbol, but in mathlib it would be written with the infimum symbol, so the same symbol as for the wedge product, because this is notation for lattices and complete lattices, and also because the implementation of filters, and I say generalized subset, this is the intuition, but the implementation, filters are collections of sets on X, and so there is this gadget filters on X is contained in the power set of the power set of X, but if you use the inclusion relation coming from the power set of the power set of X, you get the wrong order relation. And you get the wrong notion of intersection and wrong notion of union. So it really helps to forget completely about those implementation details and focus on the way I've been explaining this, which is really, again, the crucial thing is you can embed this poset by an order-preserving embedding into generalized subset, and f of x still has those intersection, so infimum operation and supremum operations, and use it everywhere. And this is what I wanted to tell you tonight.
Okay, thank you for the fantastic talk. Any questions?
I just wanted to say I totally appreciate the importance of formalizing these common arguments that we wave our hands at. And there is actually one of them in my Smooth Manifolds book. There's a problem at the end of chapter 13 that is very similar to your lemma about constructing sections of a vector bundle. Mine is a little
Great.
bigger than yours because I assume that the subsets of the fibers are open and convex and non-empty, but it's very similar.
Uh-huh. Oh, that's good. Yeah, thanks for your books, and indeed, it's yeah. I mean, I'm not too surprised to see you here because it's clear that you care about details and so being attracted to formalized mathematics is part of the game. I mean, so people yeah, interested in formalized mathematics. Of course, if you don't like details, it's hard to be interested in formalized mathematics. But I want to insist that it's also uh, liking communicating understanding is also an important part. Because when people don't give details, what you get is that the field is less easy to enter. And so I talked a lot about edge principles today. And if you're interested in those flexibility of constructions in differential geometry, your life is much easier if you have access to Eliashberg, direct access to Eliashberg, because when, of course, Yasha, he understands all this extremely well, and he would not learn anything from me explaining edge principle, but still, because all those lemmas are not stated, and some things are kind of locally wrong, but clearly not what he intended to say. It makes everything more difficult to learn if you don't have access to experts and you cannot talk to them. So that's a strong motivation for me.
Yeah, I have another question. So
Mhm.
how do you think we should formalize geometric arguments like in topology theorems where you have to compare like triangles? Those are very geometric
Ah,
arguments.
that's a good question. So we're not yet at this stage of Riemannian geometry. So we are working on Riemannian geometry with Michael Wolfgang, but unfortunately we are pretty busy but we are let's say we essentially have the Levi-Civita connection and we are very close to defining geodesics and stuff like that. And then we will need to define curvature, but this will be, again, more work. And so I haven't really thought about the comparison theorems are clearly quite a few steps uh, further away so I don't think I have anything really special to say about that. So my guess is this will work. I mean, there will be a way, but there will be a way that requires thinking. It's not only that you look at what is in the textbook, even in careful textbooks. You need to adjust a bit how you think about things and maybe have some silly abstract looking lemmas that will help tame the complexity. And so there will be mathematical work to do, and not only programming or hoping that some AI program for you. And so
Okay, thank you. Okay, if there's no other questions, let's thank the speaker again. Thank you.
Yeah. Thank you, Patrick, for the wonderful talk.
no problem, you're welcome. Bye.
Bye. Thank you.